Well, good morning or good afternoon, I guess, by the time you get this. Sorry, I'm not able to be in class today because I am staying home with my sick daughter. But I wanted to keep going. I guess we will not have a quiz tomorrow. It will be on Monday. We'll when I'm back tomorrow, we'll review a little bit and then we'll be ready for the quiz on Monday. We'll have plenty of time, so that works out. Okay. So what we're going to talk about first today is the alternate form of the derivative, and then we're going to talk about where derivatives do and do not exist, and that's kind of important to think about. Just when we're talking about where we are continuous on a line, but first let's go ahead and start with the alternate form of the derivative. Let's talk about what we talked about before here. If I were to make a graph. So the reason for the alternate form of the derivative, what we're doing is we're going to find the slope of the tangent line directly in one step. So what we've done in the last examples from the previous days is we've found the derivative and then we've plugged in an x value to find the slope of the tangent line at that point, right? And then we could use it for another point, and we use it for another point. We can do that for anywhere. Okay, so what we can do now is we're just going to use the alternate form of derivative, and we can find the slope right away at that point. But the downside is we can't use it anywhere else. We'll have to start over. Our answer is going to be a number. It's not going to be 4x or 10x or whatever, or some equation that's going to help us find it. It's just going to be a number, and that number is going to be the slope of the tangent line at that one point. If we wanted to find another one and we wanted to use the alternate form of derivative, we'd have to start all over. We'd have to start from the very beginning. So a few of you in class ask, are we ever going to use the limit? Is it ever not going to go to zero? And that was a really good question. And I said, no, not for the derivatives, but for the alternate form of derivative, yes, we will. We'll be taking the limit somewhere else. So that was a really good question, but I didn't want to confuse everybody at the time. So I kind of said, it was kind of a vague answer. Anyway, so let's say we had that example from before, and we had something that looked kind of like this. Okay. I just want to kind of talk this through. Instead of, this would be, we would call this some value C here, and here's our X over here. And then this is the group right here is just X minus C. All right. So that's as X approaches C. So C is kind of the point that we're looking at. So all I'm saying is, again, we still have that. Whoops, same go. We still have that secant line. I kind of missed, but I think you get the point. We still get the secant sign that shows that we're approaching that C. C is the point. So that's kind of just this little bonus explanation. But when we look at the alternate form of the derivative, what we're going to say is f prime at C at some point that we're looking for, not f of x, not f prime of x, f prime at the point that we're looking for. We can say, okay, that is the limit as x approaches not zero now, whatever C is. And then that is just going to be f of x minus f of C. So we're going to evaluate the function at C, and then that's what we're going to subtract out. So a little bit different. And then in the denominator, not just h or whatever, we're going to have x minus C. So this is going to make us use some of our limit skills that we used last chapter. So I hope that's working. Okay, this is going to make us use some of our limit skills. So let's go ahead and do an example. So use the alternate form of the derivative to find the derivative of 2x squared minus 5. Big distinction here. At C equals 2. Really at x equals 2. Hi, honey. You want to say hi to my class? You want to say hi to my calculus class? This is my daughter. This is the not sick daughter. This is Ava. Say hi. Wave hi. Okay, you got to go to school. Give me one right here. All right. Have a good day. Grab a snack. Okay. You didn't say hi. Okay. All right. So we're going to go at that. So let's just use what we just wrote up here in green. So we're going to find, oops. She likes saying hi to everybody, by the way. So f prime at 2 is going to equal the limit as x approaches 2 of f of x minus f of 2 all over x minus 2. So we plugged everything in just like we did to the green one there. All right, so what's f of x? Well, again, the limit as x approaches 2. Don't forget to use your limit language like we talked about last chapter. Don't lose dumb points, you know, when you're showing me all the good stuff, but you're not giving me what I need to get there. So x squared minus 5 minus, well, what's f of 2? Well, f of 2 is, let's see, 2, whoops. Yeah, 2 squared minus 5. Oh, I think that's -1. No, it's not. F of 2. Yeah, -1. All right, so that's going to be minus -1. All right, all over, again, x minus 2. All right, so hopefully you see where this is heading already. This is going to be the limit as x approaches 2 of x squared -5 plus 1 is -4 over x minus 2. What are we going to do with that limit? Right now we put it in, it would be 0 over 0. We can do something about that. I would hope everybody's brain just said, oh, that's a difference of squares pattern. So it is x minus 2, x plus 2, all over x minus 2. So we can cancel out this. I get the limit as x approaches 2 of x plus 2, which is just 2 plus 2. Without even taking my shoes off, that's 4. So what does that say in there? That is not saying that the derivative of x squared minus 5 is 4. It's saying the slope of the tangent line at x equals 2 is 4. That's the answer. So f prime of 2 equals 4. And in all this stuff, we could use all the stuff that we did for limits. You can use maybe do a I don't know, a conjugates or expand like we did yesterday, or all that kind of stuff could be in there for our limits. Okay, so that is the alternate form of the derivative. It's easier to use. It's kind of easier than the other one because, you know, it's pretty direct, but also we often only need one, so it's really no big deal. All right, let's keep going. You could also use, obviously we could do that to find the equation of the line, but we don't need it. We've done that a few times, so we don't need to do that. All right. Since the derivative of a limit is let me try that again. Since the derivative is a limit, keep that in mind. Since the derivative is a limit, for a derivative to exist, that at some point it has to be continuous at that point. Okay, not for the whole function, but just at that point, just like we talked about continuity last chapter. So remember why things are continuous. F of x exists. The limit as x approaches some point c of f of x exists. This should be a c, shouldn't it? Oops. Exists. And the limit as x approaches c of f of x equals f of c. So there's that continuity there. Slope from the left and the right point must agree. That's a bigger point. Okay, so we know continuity. We knew that. We knew if we had a, you know, if we have a jump, that there can't be a derivative there. That's pretty obvious. But what if we had a situation where we have, you know, a line going this way, and then we meet, let's say, at -1, and then we have a line going this way. It's like a piecewise function. There's no derivative there either, and we'll talk about that as we go. All right, so let's talk about the first one. Where do derivatives not exist? I got these 6 little graphs, and we're just going to give some examples of where derivatives do not exist and maybe how we're going to make that look. Okay, so let's say here for the first one, let's say we have something that looks like this, kind of a step function. I don't know if you remember that from algebra 2, I think you would have. All right, so it exists there. So the derivative here exists a lot, but it does not exist at endpoints. Derivatives do not exist at endpoints. So let's say this was, -2, let's say. At -2, it's not continuous. The derivative does not exist there. Okay, obviously you can see it's not continuous, but we can't. But the reason is, I'll talk about the reason kind of more tomorrow. But the thing is, it's not locked in. The derivative is a slope, right? Where would I put the line? It doesn't make sense. So that's how we'll do that. We'll talk about that more later. All right, let's go on to this one. How about, what if we had an equation like this, where we obviously have an asymptote at 0. So we would say the derivative does not exist at asymptotes. Okay, so we would say here, we are good from -infinity to 0, 0 to infinity, but we do not exist at 0, nothing at 0. So I want you to say it with interval notation. All right, this would be like this kind of function right there. That's what that is. All right, so something like that. That would be, so nothing at endpoints, nothing at asymptotes. The next one, this will be kind of a new concept. Nothing at cusps. Not really new. Cusps are formed from, oops, when we do, let's say, an absolute value equation. Okay, so let's say this is and they also do it with some of the like, they sometimes will look like this. So this would be like a cube root kind of a question, or an odd root kind of a question. So here and here, so let's say this is at -4, this is at 5. Let's say we had these two functions. For the first one, we would say, again, -infinity to -4 union -4 to infinity. We would say the reason is no derivatives at cusps. We call those cusps. And it would be the same thing, not at 5 on the other one. Just doesn't work there. All right. Kind of looks like a seagull a little bit, doesn't it? All right, let's go on to the next one. I had to put these on my phone. All right. Again, not at endpoints, but let's say we had this function. Let's say we had y equals the square root of x minus 1 plus 2. All right, so that's up 2 and over 1. That would be a rational function there. So we would say not at endpoint and not anywhere. So here we would be good at, again, not at endpoints. So here we would say, okay, the derivative is okay from 1 to infinity, going on and on and on forever to the right. But at 1, it can't be there either. It can't be there either. And again, how would it lock in? How would it? We'll talk about that more tomorrow again, like I said. But how would we make that work? Now, here's along the same lines. We can't do it at turning points. So what if we had something called y equals, let's say, the cube root of x? So that's going to look like this. And since it's an odd root, it's okay the other way. So maybe something like this. So we're good on almost everything except right here. So the derivative does not exist at a turning point. So what that means is, on the right side is the positive side of this. On the left side is the negative side. And on that turning point, that's where it's neither positive nor negative. And again, we can't lock it in there. So it really doesn't work that way. Okay, so right in the middle, that's called a turning point. We can't have it there. All right. And one more. And this one's pretty obvious. Let's say we have a jump. Well, we're obviously not continuous in there, so we would say not at jump, not differentiable at a jump. Obviously, we're not continuous. We can't that work. So let's say this is at what, -1, let's say. So we would say we are differentiable from negative infinity up to -1. Can't include -1. So -1 to infinity. All right. So yeah, so those are just kind of some examples. What I'll do on a quiz or test, I'll give you a graph and say, hey, where is it differentiable? Where is it not? So a function is differential. That means it's continuous at that point. But just because it's continuous doesn't mean it's differentiable. The one right above you would say that it is, that's continuous, but when it has that turning point, that's no good. When it has a cusp, that's still continuous, but it doesn't mean that it is, you can do the derivative there. Yeah. Okay, so let's look at these functions and see what we can talk about. So yeah, we'll do that later. Okay, so describe the value of this function. Well, we know this is one of those that's going to kind of look like, we're on for the first one. We know it's going to look like, we've got an asymptote at 2, right, and at 0. So we know it's going to do this and this. So where it is, so f of x is differentiable at negative infinity to 2 to infinity. We know right here is where it blows up, where we have an asymptote. 2/3. Let's graph that. That's going to be a cusp. I'll just tell you since we're working here. And it's going to be at 3. So 1, 2, 3. It's going to make a cusp that goes boom, boom, like that. So at the cusp, at this specific point, we cannot take the derivative there. We cannot find a correct derivative there. So that would be f of x is differentiable from negative infinity to 3, but not at 3, but then up to infinity. All right. All right. The next one is a jump. Just without going into it, but you can see it's obviously a jump because we raise up 3 after being, it's the same function, but just with a vertical shift on it. So at 2, we would say there's a jump. Not, yeah, let's just say where it is. So it is differentiable. F of x is differentiable from negative infinity to, looks all the way to 2, right? All right. And then the last one is x plus 4, square root of x plus 4. So that would be one where, hey, we know where that starts. It starts over at -4, and it does one of these. So we are differentiable from -4 to infinity. Nothing to the left because the function doesn't even exist there. So we can't have anything there, and not on the endpoint. So we can't because of the endpoint right there. Okay, I think we're done for today. Like I said, no quiz tomorrow. We'll have a big review day. Plan on going to the boards tomorrow. And then we will we'll move on. Oops. We'll move on to, we'll finish up this stuff, and then we'll move on to the other derivatives after that. All right, have a nice day, and have a nice day.